Hello friends, welcome to VK lectures. In this lecture we will be discussing about method of images, how to solve problems based on the method of images, and we will also be looking at the applications of method of images. Here is a small description about the method of images. Method of image is a technique used in electrostatics to solve boundary value problem involving conductors and dielectrics. It is useful when dealing with conductors in presence of other conductors or boundaries. The method involves introducing image charge to simplify the problem. Here we can find out the electric field V and electric field E, the potential V, and the uh, um, charge density rho, and the sigma. Now here is the actual method given, how the method of images work, what are the steps involved in method of images to solve electric field problem, boundary value problems, etc. Now here we have a conductor. This is conductor which is grounded. Now here we have placed a charge q. Now let that distance from which the charge q is placed from the conductor be x. Then how to do the uh, image of this? The problem is nothing but here this is the point x, this is the charge q. Now towards the, now we have to replace this conductor by an imaginary extended boundary. So this is the imaginary extended boundary, imaginary boundary which acts like a mirror. So on the left this image will be placed which is at a distance x dash, and the charge is q dash. Now here our aim is to find what is x dash and q dash, which is the image distance and the image charge. So q dash is the image charge and x dash is the image distance. This is the real charge and this is the distance x. So once again the method is replacing the conductor by an imaginary extended boundary and consider the image charge for each real charge. So here is the image charge. So how many number of real charges are there? Corresponding to that there should be equal number of image charge, and those image charges will be placed at an equal distance as that of the real charge. Here are two examples. First one is I am placing it, this is the spherical conductor, and I have placed a charge at a distance, this is from the conductor at a distance x. I have placed a charge q for with let the radius of this spherical conductor be r. Then we can consider a charge, imaginary charge. This is the capital R is the radius of this sphere, imaginary charge somewhere here, which is q dash, which is at a distance of x dash from the center. So this distance is x dash from the center, and we have the real charge somewhere here, which is q, which is at a distance x. The total distance can be considered as the d. From the center to that point. Similarly, we have another uh, question. The first one is at a distance uh, x1. The second charge is at a distance x2. Then we have to draw an imaginary extended boundary, and two charges has to be placed at equal distance. This is q1, this is q1 q2, q1 q2, this is q1 dash, and this is q2 dash, which q1 dash and q2 dash are the imaginary charge for q1 and q2. Now uh, let's consider a different scenario where you have two conductors, C1 the conductor 1 and C2 conductor 2, both are connected to the ground. Now we have a charge q, which is at a distance x from the conductor 1, and the other one is at distance y from conductor 2. Now this is EM1, the mirror, which is corresponding extended boundary, that it gets extended boundary corresponding to the conductor 1, and here you have EM2, which is the mirror or the extended boundary corresponding to the conductor 2. So somewhere here we have our charge q and its imaginary charge on m1 and m2. This is at distance x. So here also at distance x we have q, same charge q. Now with respect to m2, this distance is y, and exactly at y distance you have q, or let's write this as q1 and this is q2. Now again its imaginary charge, that is q1 imaginary charge and q2 imaginary charge, will be at this point, which is again q4. Sorry, this is q1, q2 and q3. So there are one real charge and three imaginary charges. You have to note that this angle between the two conductors is 90 degree, and for two conductors placed in this way, so this is C1, this is C2, at some angle, let's say theta, then number of image it can be formed. This you might have done in your lower classes when two plane mirrors are kept inclined at some distance, just like you see in hair salon. If you place a object here, number of images formed, so number of images formed will be equal to 360 divided by theta minus 1. So if this is again, if theta can be written as pi by or yeah, pi by n, then it is 2 pi divided by pi divided by n minus 1. So that's equal to 2n minus 1. So 2n minus 1 number of images will be there, or you can simply write 360 by theta minus 1. Method of images due to a conducting plane. Now this is the conducting plane that we are talking about, C, and it is being grounded, and a charge Q is placed at a distance say for example D. Now this one is the uh, extended imaginary boundary. Let's name it by M. Then here we have our charge Q, which is placed at some distance D. Now we need to find out the position of the uh, image, that is Q dash, and X is the position, and value is value of the imaginary charge or image charge, not imaginary, it is image charge, and image charge and the position of the image charge. This is what we need to find. Now to find that, we have to consider 2 points. Let's say for example P1 and P2, and we know that at P1 and P2 the potential is 0, because it is on the conducting plane. On the conducting plane, potential is 0. Now because this is being grounded, so it is 0 potential. So on the conducting plane the potential is 0. That means at P1 and P2, any point on the imaginary extended line, and the potential is 0. So let's call this as VP1, that is the potential at P1 is 0 and the potential at P2 is 0. Solving these two equations, finding out the potential value and equating, we will get the values of X and Q dash. Now what we are doing is, we are removing this plane and replacing it with a image charge, such that VP1 and VP2 are 0. So let's once again do that. This is a charge Q, which is placed at a distance D from the center, and this is Q dash, which is at a distance X from the origin. Now this distance is Z. Now let's take this is point P1 and point P2. Now VP1, the potential at point 1 is 0, which implies that the potential, so that is K small q by D plus the potential at P1. This can be written as potential at potential due to Q plus potential due to Q dash should be equal to 0. So potential due to Q is KQ by D, and potential due to Q dash is KQ dash by X equal to 0. Now this implies that Q dash is equal to uh, Qx by D. So Qx by D with a minus sign. So when you take it to the other side, it becomes minus. So minus Qx by D. Now here at potential at P2 is also 0. That means uh, uh, potential at P2 due to VQ1 and VQ and VQ dash. So this X and Z, so this value will be equal to X square plus Z square. This is root of uh, D square plus Z square. So KQ by at this point, so KQ by a distance is root of D square plus Z square plus KQ by or KQ dash by root of X square plus Z square equal to 0. Now KK gets cancels. Now what we can do is now we can write it as Q divided by root of D square plus Z square equal to minus Q dash divided by root of X square plus Z square. Now what is Q dash? Q dash is nothing but minus Qx by D. Now that's so minus Qx by D into 1 by root of X square plus Z square. So rewriting it, we get Q divided by root of D square plus Z square equal to, so this is minus, so minus of minus, this become plus, so that's equal to Q x divided by D into root of X square plus Z square. Here we can cancel out the terms Q and Q, and what we get is from here we get bring this X to the denominator. So what we have is 1 by X times root of D square plus Z square equal to 1 by D times root of X square plus Z square. Here we can see that the X position, here position at X is replaced by D, and similarly the position of D is replaced with X, which means X equal to D. And hence we have proved that X equal to D, and we also know that Q dash equal to minus Qx by D. Now substitute X equal to D here, so d by d becomes minus equal to 1, and from this q dash equal to minus q. So we have four conducting plane x equal to d, or you can write uh, image distance equal to uh, charge distance or charge position. Image distance, image charge, you can write here image charge distance, and the image charge equal to minus of the real charge, or you can write here real charge distance. So image charge distance equal to real charge distance, and image charge equal to minus of the real charge, that is x equal to d. Remember that x is the image distance and real charge distance is the d, and q dash is the image charge and q is the real charge minus q for conducting plane. Method of images for conducting sphere. So here we have placed the charge uh, q, uh, and this is having a radius capital R, and 2 points we have to consider. So it's to the axis along which the center and the point charge q passes. So we can consider 2 points p1 and exactly opposite p2, where on the conducting sphere where the potential is 0. Alright, now the imaginary charge will be within the sphere. So let's see where the image charge will be. This is capital R, which is the radius. So image charge will be somewhere here, which is q dash. So uh, q dash, and you have somewhere here the q, and we need the distance. The distance is considered, d is considered from let's take it from this point, the center to the point charge q. So from this point till this distance is d. So here the distance is d. That means from the center to the point charge. Now here we have q dash, and from the center till the distance q dash we can write it as x. So this distance is x. So we have considered 2 points p1, and this is p2, where the potential is 0. So let's write down the potential at point p1 equal to 0. So potential due to q and q dash. So potential due to v q plus vq dash. This is at point p1. Okay, vq plus vq dash. So k q by the distance of point p1 from q. So this distance is what we need. We know that from this point to this point is d, and if you remove this distance, that is the radius capital R, you get distance from p1 to q. So it is d minus r plus the potential potential due to q dash, that is q dash due to this point at this point p1. So if this distance is x and this distance, the entire distance is r, it will be r minus x. So k q dash divided by r minus x should be equal to the 0. We can simplify this. Q divided by d minus r equal to q dash divided by r minus x, and from these two from this equation we can find q dash is equal to r minus x divided by d minus r that is equal to into q. So q into r minus x divided by d minus r. Now let us take the case of point P2, where this distance is r, and again this distance is r, these two distance, and from this distance to the point charge q is d, and here you have q dash, and from this distance is x. Now at point P2, potential at point P2 is 0. So this implies that potential due to Q at point P2 plus potential due to Q dash at point P2 is 0. So that's equal to KQ divided by this distance is d and the other distance is r. So d plus r plus kq dash divided by, now we need due to this q dash, so this total up to here is r, this distance is x, so r plus x. So let's write x plus r equal to 0. Now from this we can write the value q by d plus r equal to minus q dash divided by x plus r. Now we already have got what is q dash, or now let's write before that q dash is equal to minus let's write here q dash is equal to x plus r divided by d plus r with a minus q, so minus q into x plus r divided by d plus r. So this is the second equation for q dash. Earlier we have got q dash is equal to q times r minus x divided by d minus r. So this is the two formula that we have got. Yes, of course, here also we have a minus sign. Now these are the two equations, equation 1 and this is equation 2. Now what we need to do is to equate them. So q into r minus x divided by d minus r is equal to q into minus and minus, we can cancel it out, x plus r divided by d plus r. Now this gives us that r minus x times d plus r equal to d minus r times x plus r. If you substitute, simplify this equation, we will get x in terms of r and d. So let's do that. Now let's expand this. R times d is rd, r plus, that is plus r squared, minus xd minus xr equal to dx plus dr minus rx minus r squared. Now let's cancel out the common terms. Rd and dr gets cancelled. Minus xr, that's minus xr here, minus rx here. So r square minus xd. So this becomes 2xd. So that's 2r square equal to 2xd and r square equal to xd and x is equal to r square by d. So this is the value of x. Now we can take any one of the equations, that is q dash equal to q into r minus x divided by d minus r. And with this equation, let's substitute for x. So that's the first part. X equal to r square d, r square by d. So q dash equal to this, there is a minus sign. Q minus q into r minus r square, x is r square by d divided by d minus r. Now that's equal to q dash minus q dash into dr minus dr square divided by d minus r. Now that's equal to minus q dash, let's take r outside, r into d minus this is divided by d, dr minus r square divided by d. So if you take r outside, it becomes d minus r divided by d divided by d minus r. So d minus r gets cancelled. So this becomes minus q dash into uh, d minus r and d minus r get cancelled, minus q dash r divided by, sorry, not q dash, minus q, minus q r by d, because d minus r and d minus r gets cancelled. So d minus r and d minus r. So that's equal to q dash. So we got, for conducting sphere, value of x equal to r square by d, and the image charge is equal to minus q r divided by d. Here we have to remember that r is the radius and d is the distance of the point charge or the real charge from the center. Here is one application of method of images. We are going to solve one application, that is to find the force between charge and the conductor. Now assume that we have a charge q here, and this is the conductor which is being grounded. Then we are asked to find the force on q. So the question is, find force on q due to what is that, the conductor. So this is the imaginary extended line, and this is your charge q, and since it is a plane conductor or conducting plane, since it's a conducting plane, our imaginary charge q dash is equal to minus q, and the position of this position x equal to d. So this distance is d. Then the force on q due to conductor is same as force on q due to minus q or q dash. So if we have a conducting plane like this, the force exerted by this conducting plane on the charge q will be same as the force exerted by this uh, imaginary charge on the charge q. So now we can find the force using the Coulomb's law. K q is minus, so let's draw one line on the charge on which we are going to find the force. So since it is minus and this is plus, this is attractive, that means towards, so it will be this charge will be pushing it towards it. Okay, now that means it is in the negative I direction. This is I direction, this is j direction, positive j direction, this is plus I direction, and you have below it is negative j direction. So k q q by x and d are same, so you can write x plus d is nothing but 2d whole squared. So since we can write kq square by 4d square with minus I cap, that means it is in the negative I direction. The force is along negative I direction, that means the force is in this direction. Find the net force on 2q. This is our question. Now here we have charge q, and this is 2q, and this is d, and this again d. The separation between the charges is d, and separation of the q from the conducting plate c is also d. Now according to the method of images, for conducting plane, q dash is equal to q, and q double dash, sorry, it's a minus q. Let this be q dash, and this is q double dash. This is q, and this is 2q, and the force on 2q is what we need. That means what is the direction and the magnitude of force acting on 2q. So q double dash is minus 2q. So we got the charges. This is 2q with a minus sign, and this is minus q, and the separation is as same as d, because for conducting plane the separation do not change. So now we need the separation of 2q from other charges. So 2q from this particular charge is at a distance of d, and from q dash or minus q, the separation is we'll write it like this, which is d, again another d, and another d, which means there are 3d, and separation from q dash to 2q is 4 times d. So we have to find the net force, the force due to charge q, q dash, and q double dash on 2q. So let's take the first charge. Let us number them as 1, 2, and 3. So let's calculate F1, that is force due to charge 1, is equal to K 2q into q, 2q into q divided by d squared, and this is positive charge, this is also positive charge as per the given question. So positive and positive, it repels, so this charge will exert a force in this direction. That means F1 is in the positive I direction, so we will write plus I. Now we need F2, the force due to charge 2. So K charge 2 is minus q, but we need to write only the magnitude here, q, and again in 2q into q divided by the distance is 3d, so 3d squared, and what is the charge? This is minus and this is plus, minus and plus. So it is attractive force, so it will attract towards the uh, so this is F2 attract force, and it's minus I direction, so minus I. Now we need F3 K 2Q into Q double dash is again 2Q divided by 4D squared, and there is a minus charge here, is minus, this is again plus, and minus and plus again attractive force F3. So F1 is in the plus I direction, F2 and F3 is in the minus I direction, so this is minus I direction. So the net force F will be F1 plus F2 plus F3. So K2Q KQ square, so 2KQ square by D square is can be taken common, then 2K Q square D square plus I, then plus, sorry, there's a minus sign, 2KQ square F2 we have to write 9 1 by 9 1 by 9 and wait a minute, you can also take down I cap. I cap is also common because it is only along the x direction, so 1 minus 1 by 9 minus this is 2, if you take 2, 16 will be there, 2 by 16 is 1 by 8, so 1 by 8, so that's minus, sorry, I 2KQ square by D square into 1, this is 9 and 8, 72 minus 9 minus 8, so 72 minus 9 minus 8 divided by 72, so that's equal to 2KQ square by D square into 17 minus 72 minus 17, 55 by 72 in the direction of I cap. That means the net force is in the positive I direction, which means that the repulsive force due to the first charge, which is very near to 2Q, is more dominant than the other charges. Here is a question for practice. Find the force on minus Q. This is the charge for which you have to find out the force. For the charge minus Q and Q placed at a distance D and 2D from a grounded conducting plane. Okay, so you can work this problem. Here is a task for you. Find the force on charge Q. So this is this FQ, and there are two conducting plates, that is C1 and C2, both are grounded, and net force on FQ is to be analyzed. Either the force will be in this direction or towards this direction, that is away from center. This is away from center, and this is towards the center is here. So this is from the conducting plate A, C1, it is at a distance of A, and similarly from the conducting plate C2 it is at a distance A. So find the net force on charge Q. Find the force on charge Q placed at a distance of 2r from the conducting plane, conducting sphere of radius capital R. Now we have to find an equivalent model with replacing conducting sphere with real image charge at certain distance. Now these two quantities, the where we have to place the image charge and what is the charge of the image charge, that two things we need to find out. Now the image distance or image charge distance is given by x. Before that, let's somewhere here, let's say we have the x, and this is q dash, that is the image charge. Okay, now q dash and x, x is the distance from the center to the point q dash where the q dash is placed. So we need to find the image distance, that is x and q dash. So x is given by capital R square divided by 2 times d. It's r square by d, not 2d. So r square by d, and d is equal to 2r, and r is nothing but the radius of the conducting sphere. So that's equal to r square by d. D is 2 times r, so 2 times r. So this is d, distance from the center to the point where q is placed. So r square by 2r is nothing but r by 2. So x is equal to r by 2, and the image position, image charge is given by minus q dash is equal to so q dash is equal to minus q into capital R divided by d. So this is the charge of the image. So that's given by minus q, r is as it is, d is 2 times r, that's equal to minus q by 2. So now we need to put q dash is equal to minus q by 2, and this distance is r by 2. So now force on q is what is being asked, that means force on this particular charge. So since it is minus, let's write F is equal to force on q is equal to k q dash divided by uh, uh, let's write r square, that's equal to k q q dash is equal to minus q by 2, or let's write the magnitude q by 2 divided by, now the distance between q dash and q, this is x is r by 2, so this also will be r by 2 because total distance is capital R, and this is r, so r plus r by 2 is 3r by 2, so 3 capital R by 2 whole squared. So that's equal to k q square by 2 into 9r square by 4, 9 capital R square by 4, so this becomes 2k q square divided by 9r squared. Yeah, so this will be this is negative and this is positive, the force will be force of attraction, so it will be towards the minus I cap, so minus I cap. This question can be taken as a practice question for you. Find the force on charge q. Somewhere here we have charge q placed at a distance of 3r. So that means from the center to this distance is 3r. From a conducting sphere of radius 2r, and this radius is 2 times r. So calculate the force on charge q, that is fq. Find fq. Method of images application. One of the application is finding the work done. Now we have the conducting plate here, which is grounded, and if you place a charge here q, there will be q dash, which is equal to minus q, and if this separation is d, then again here also the separation will be d. Now to find out the work done, we have the formula for work done. Work done W can be written as minus integral f dot dr from infinity to point r. Now here this r can be replaced by minus integral infinity to d distance from the conducting plate, so f dot dr. Now we need to calculate the work done. Before that we need to find what is the force on q. Now to understand the force on q, it's simple. Here this is the charge q where we have to find out the force. So here we have minus q, and the distance of separation from minus q to q is 2d. So force is equal to k q by 2d whole square in the direction of, since it is minus, it is attractive force, so it's negative I. So that's equal to minus kq square by 4d square I cap. So now we need the work done, f dot dr or f dr. So the integration integral, we can write r in terms of d in terms of r, so minus kq square by 4r square dr. So that's equal to, and we are finding minus of minus integral from infinity to r or infinity to d, minus kq square by 4r square dr. So that's equal to kq square divided by 4 into minus 1 by r, moving from infinity to d. So putting the lower limit first, we have kq square by 4. The lower limit is 1 by infinity minus 1 by d. So that's equal to 1 by infinity is 0. So minus kq square by 4 times d. So that's the work done. Here is a small technique or alternate method to calculate the work done. So alternate method to calculate work done is, so now here we have the charge q placed at a distance d. Then its image charge will be minus q, which is at a distance d from this extended imaginary line. Now we have got the work done from the formula minus integral f dot dr. That's according to the previous calculation. The work done is kq square by 4d with a minus sign. Now alternate method is the potential energy. Work done is nothing but the potential energy, not the potential energy. Work done and potential energy. So potential energy is equal to potential energy by method of images. By method of image, you can find the potential energy using the two charges into number of given charges by total number of charge. Number of given charge by total number of charges. So potential energy by method of image can be calculated as k q minus q by the distance, that is 2d. So that's equal to minus kq square divided by 2d. Now the potential energy, actual potential energy, is equal to method of images, the minus kq square by 2d into number of given charges. Number of given charges is 1, and total number of charges is 1 and 2, including real and imaginary charges. So 1 by 2, that's equal to minus kq square by 4 times d. So that's the work done or the potential energy. Here is another application of method of images. The application is work energy theorem. Now what is work energy theorem? The sum of the kinetic energy and the potential energy remains constant. That which means the total energy is conserved. It comes from the conservation of total energy, total mechanical energy. Now what is the application here is, we have a charge, real charge q, placed at a distance of d from the grounded conducting plate. Now due to this, we have a minus q charge produced, which is again at a distance d. Now we have seen that the force of attraction, or the force, is equal to k q square divided by 4d squared in the direction of minus I. That means there is a force exerted by this grounded conducting plate on this charge minus charge q, which means the charge is attracted towards the grounded conducting plate. Now as there is force, the charge will start moving towards the conducting plate. So charge, as the charge moves towards the conducting plate, after some time t, the charge reaches say for example this particular point. So now the position of the charge, that means this particular charge q, is this. Now this will be some d minus x. We say that let it be x, so that the total distance covered by the charge q in time t is d minus x. So this, if this is x, this should be d minus x. Now similarly, when the charge q is at a distance x, the imaginary charge will be produced here, which is again at a distance x, and this is minus q. So as the charge q moves from d to x, the minus q, that is the image charge, also will move from d to x. So in this process, there is an initial energy, sum of the kinetic energy and potential energy, that is potential energy initial plus the kinetic energy initial equal to potential energy final plus kinetic energy final. So sum of the kinetic energy and the potential energy is equal to a constant. So here we can write, instead of PEI, VI, and the potential energy can be written as KI. This is equal to VF plus KF. So this is what we are going to prove here. So here we have the entire distance d. So this distance is x, and here also we have the x distance. Now the potential energy initial, this is what we are going to check. Initial potential energy, that's equal to VI. So VI equal to VI method of images through method of images into 1 by 2, that is number of given charges by total number of charges. So that's equal to VI by method of images, means there is a distance is 2d, so kq square by 2d into 1 by 2, that's equal to kq square by 4d. Now the kinetic energy initially the charge q is at rest, so the initial kinetic energy is 0. Now Vf, the final is V VREF method of images into 1 by 2, so that's equal to Vf method of images, that's kq square by 2 times x. So now this distance is 2x, so 2x into 1 by 2, that's equal to kq square by 4x. Now the kinetic energy final is equal to, we are writing it as half m v square because we are unaware about what is the velocity. Now according to the work energy theorem, we can write the sum of the kinetic energy and potential energy in the initial stage, that is Vi plus Ki equal to Vf plus Kf. So that's it. Vi is kq square by 4d plus 0 equal to kq square by 4x plus half m v squared. From this we can write half mv square equal to kq square by 4 into 1 by d minus 1 by x. So 1 by d minus 1 by x. Here we have to consider the initial energy, the potential energy to be minus. So here also it is minus, this also minus. Okay, so minus and minus. Now we can write and now it becomes minus half mv square. Now 1 by d is 1 by d minus 1 by x will be a negative quantity, and minus kq square by 4d is also minus quantity. That means half mv square, kinetic energy cannot be negative. So due to this negative sign, we have brought the kinetic energy term positive. So just multiplying by m, so we can write it as v squared, that is velocity is equal to kq square by 2 into 1 by x minus 1 by t. So this is the velocity squared. So velocity will be equal to kq square by 2 into 1 by x minus 1 by d to the power half. So this is the velocity at x. We have missed out a quantity here. This is m, so m will come here. So this is m. So kq square by 2m 1 by x minus 1 by d to the power 1 by 2. Find the velocity of the charge q at a distance d by 2 when the charge q is placed at a distance of d from the grounded conducting plate. So here we have the formula v equal to kq square by 2m 1 by x minus 1 by d to the power 1 by 2. So we have the values x equal to d by 2. Okay, so this is the distance x, so that is given as d by 2. Now just substitute the values. So kq square by 2m into 1 by x is 1 by d by 2 minus 1 by d to the power half. So that's equal to kq square by 2m 2 by d minus 1 by d is 1 by d, so it's 1 by d to the power 1 by 2. Again, just if you want to simplify, k can be written as 1 by 4 pi epsilon naught 4 pi epsilon naught q square by 2m into 1 by d to the power half. So here again 1 by 4 pi epsilon naught, so that's q square by 8 pi epsilon naught md 8 pi epsilon naught md to the power half. So this is the velocity at d by 2. Here is a question for practice. Find the velocity of the charge q at a distance d by n when charge q is placed at a distance of d from the grounded conducting plate. So this is the distance d from this grounded conducting plate to this point where the charge is placed, and after some time t our charge q reaches d by n. The n can take values from 1 to sorry, not 1 means here 2 3 4 etc. That means some fractions of d. So when the charge moves to d by n, what is the velocity? This is the question. You can use the same formula. V is equal to kq square by 2m into 1 by x minus 1 by d whole to the power 1 by